In this video, I want to go over an example problem of calculating equilibrium constant. I have a equilibrium or a reversible reaction shown here of hydrogen and iodine forming hydrogen iodide. And I've, let's say, used UV-vis spectroscopy or some other technique in the lab, and I've been able to decide what the concentrations of each of these reactants and products are at equilibrium. When the reaction no longer seems to be changing concentration. So I can calculate the equilibrium constant at this point. So just looking at the information I have and comparing, I have my reactants here, and they seem pretty small. They're only 0.58 molar, and my products are much more concentrated at 14 molar. And so I'm going to expect that my reaction will favor products. This would mean an equilibrium constant greater than 1. So I'm going to keep that in the back of my mind as I do this calculation. So setting this up, I'm going to write out my equilibrium constant expression. It's that K value equal to the concentration of my products over the reactants. So in this case, my product is hydrogen iodide. And I have a coefficient of 2 in front of it. And so I'm going to square that concentration of hydrogen iodide. It's going to play a larger role in figuring out where equilibrium lies because it forms 2 instead of 1. And I'm going to divide that by the concentration of my reactants multiplied together. So that's my hydrogen and my iodine. Now, my coefficients here are 1 because there is no coefficient written. So this would be to the power of 1, which is the same as itself. So 2 to the power of 1 is 2. So now I'm going to plug in the values that have been given to me. I have 14.3 molar squared divided by 0.575 molar times 0.575 molar. And plugging this into my calculator, I'm going to get a value that's about 16 or 618. Now, I don't write units on this because all my units have canceled out, actually. So equilibrium constants are a unitless value. And evaluating it, 618 is definitely larger than 1. And so that meets my expectation that I'll have a large equilibrium constant. Now that we know our equilibrium constant, that will apply at the same temperature to any reaction I set up for hydrogen combining with iodide at different concentrations. And so I can use it to predict the amount of product I might form if I know how much of my reactants I'll have at equilibrium. We actually have a way of predicting the amount that will form from the amount I start with of my reactants, but we will save that for another class. Now that I know that K equals 618, let's rewrite our equation here. So we've got equilibrium constant of 618 for our reaction between hydrogen and iodine, forming 2 hydrogen iodide. Let's say at equilibrium, I know that my reactants are actually quite a bit less concentrated. Let's say that my hydrogen and my iodine have the same concentration, and it's actually now 0.0125 molar. Well, I can use this information to figure out what that concentration of hydrogen iodide I have in solution is. So I'll set up my equilibrium constant expression again, as I did before, with my products to the power of the coefficient in front of them over the reactants. And now I'll plug in the values that I know. This time I do know K, it's 618. I don't know the concentration of my hydrogen iodide. I'm curious about that. And I know the concentrations of my reactants. And I'll plug those in here. And now I could solve for that hydrogen iodide concentration. It's going to be 618 times this 0.0125 times 0.0125. And that'll equal the square of hydrogen iodide. To get rid of that squared and isolate the concentration of hydrogen iodide, I'm going to take the square root of both sides. So that on my right side, that's going to leave just hydrogen iodide concentration. And this value on the left, I'm going to plug into my calculator. I get a value of 0.31 molar. So this is still much larger than our 0.0125 molar for our reactants. So it makes sense because that K value is larger than 1. I should have a higher concentration of products than my reactants. But we're doing this on a much smaller scale at a much lower concentration. And so my concentration for my hydrogen iodide is a lot less than we calculated in the previous problem.